Good day. In this video, we will be discussing the answers to assignment 9. Let's have a look at question 1. In part A, we want to use theorem 105 to explain why the surface 3x plus 2y plus z equals e to the power xyz have a tangent plane at the point 0, 0, 1. And then we want to give a Cartesian equation for this plane. Alright, so we're doing multivariable calculus, so we need a function. So let's start off by defining the following function. Let g be a function of three variables defined as 3x plus 2y plus z minus e to the power xyz. So the surface that we are studying is when g is 0. So the surface is when g equals 0. So now we have a function of three variables. G is equal to 0. Alright? And is a point on the surface? Well, note that g naught naught 1 evaluates to naught plus 1 minus 1, which is 0. So the point is on the surface. Element of S being the surface. And now let's calculate grad g. So g is a function of three variables, so grad g is a 3D vector. The first component is 3 minus yz e to the power xyz. The second component is 2 minus xz e to the power xyz. And the third component is 1 minus xy e to the power xyz. And we see that grad g at this point, 0, 0, 1, evaluates to the vector 3, 2, 1. All right. Now, they want us to use theorem 105. So, are the conditions met? Well, note that since gx, gy, and gz are continuous on R3, and grad g is not the zero vector, we can use theorem 105. And by theorem 105, it follows that near the point 0, 0, 1, g is a differentiable function of two variables, and hence a tangent plane exists. So what we've done in part A is that we have proven that yes, there is a tangent plane at this point. And now part B, we want the equation of the tangent plane. Alright, so let's start with part B and say T is this tangent plane. And now we have a nice formula, and the formula says that if the point xyz is on T, that happens if and only if grad g at that point dotted with xyz minus the point 0, 0, 1 equals 0. And so this happens if and only if grad g is a vector 3, 2, 1. This is the vector with components x, y, z minus 1 equals 0. And this happens if and only if 3x plus 2y plus z equals 1. So, a answer is 3x plus 2y plus z equals 1. And that is the end of question 1. So, just a straightforward application of theorem 105. Alright, let's move on to question 2. Now question 2 has two parts again. So consider the function of two variables, and we want to calculate the directional derivative of f at a certain point where the angle is pi over 6. So, well, let's start off by saying, well, I know what grad f is. F is a function of two variables, so grad f will be the following 2D vector with components f partial x and f partial y. So differentiate partial x, we end up getting x and partial y, we end up getting y squared. Alright, but now if the angle is pi over 6, we get the unit vector u, which is given by cos pi over 6 sine pi over 6. And cos pi over 6 is the value root 3 over 2. Sine pi over 6 is the value of a half. Special angles, you got to know them. And so now we can say that the directional derivative of the point minus 1, 1 of the function f in the direction of pi over 6 is u dotted with grad f at the point minus 1, 1. And so this now becomes u is the unit vector with components root 3 over 2, a half, and grad f at the point minus 1, 1, plugging in there, becomes the vector minus 1, 1. And if you dot these two vectors, you end up getting the value 1 minus root 3 over 2. So that was very easy. We have this neat formula to work out the directional derivative in terms of a unit vector and grad. But part B is a bit more tricky. Let's read the question carefully. Find the set of points in which the direction of the fastest change of f is in the direction of the vector alpha plus 1, 3. So for my solution, I'm going to do the following. I'm going to take alpha is equal to 1. So the vector alpha plus 1, 3 becomes the vector 2, 3. Maybe you have a different value of alpha and your answer will look different. Alright, now I've underlined the word fastest change. Alright, so we need to know in what direction is the directional derivative has the fastest change. And so to get the fastest change, alright, that means that we've got to travel in a certain direction. And that should remind you of one of the theorems in chapter 3. And the direction in which we get the fastest change, that will be grad f at the point xy. Alright? So let's make it a bit more clear. So take the point xy, and by theorem 98, the fastest change is in the direction grad f at that point. Alright, and so we want the fastest change to be in the direction of the vector alpha plus 1, 3. So it means they must be scalar multiples of one another. So we want the following. We want that grad f must be a scalar multiple of the vector 2, 3, where k is positive. Alright, and so we proceed and now we do the following. So grad f we've worked out is the vector xy squared, and this now becomes the vector 2k, 3k. Alright, so if these two vectors are equal, then this means that x is equal to 2k and y squared is equal to 3k. And now remember, k is positive, so 3k is y squared, so that makes sense, and x is 2k. Alright, now to make our lives easy here, we want to eliminate k, and so that means the following, that since x is 2k and that's positive, we get that k is x over 2, and that's also equal to y squared over 3. So thus, if we rearrange, we get that 2y squared is equal to 3x, and x is positive. And so now we can say the set of points are, and we can write this in set notation. So S is the set of 2D vectors x and y, where 3x is equal to 2y squared and x is more than 0. And that, ladies and gentlemen, gives us all the set of points where the fastest rate of change is that specific vector. So again, here we got to use theorem 98. Great. So now let's move on to question 3, which was the last question on this assignment. Now in question 3, it again has two parts. Now here we have a function of two variables, and in part A we need to find all the critical points. And what makes this one interesting is that we get an example of a function of two variables that has an infinite number of critical points. So how do we find critical points? We need grad f. So grad f is defined as, it's a function of two variables, so grad f will be the vector where the first component is f partial y and the second component is f partial z. So in this case, f partial x turns out to be cos x, and f partial y turns out to be minus sine y. So for critical points, we want this to be the 0 vector. So we want all pairs xy such that cos x equals to 0 and minus sine y equals to 0. So we need to find the general solution of all 2D vectors such that cos x is 0 and minus sine y is 0. Alright, now this is back to first year. Now if you solve cos x equal to 0, then you see that either x is pi over 2 plus an integer multiple of 2 pi, or x is 3 pi over 2 plus an integer multiple of 2 pi, where k is an integer. And if you study the sine curve, then we see sine y equals to 0, then y is equal to pi r, where r is an integer. So cos x is 0 at pi over 2 and 3 pi over 2, and then you just add integer multiples of the period. And the interesting thing about looking at sine y equal to 0, it happens when y is an integer multiple of pi. So I'm using two different parameters, k for cos and r for sine. Great. So I'm going to write this now in set notation. So S is going to be the following. It is going to be all the 2D vectors of the form pi over 2 plus 2 pi k by r, where k is an integer, r is an integer, union, and it's also going to be all the pairs where x is 3 pi over 2 plus 2 pi k by r, where k is an integer and r is an integer. So we see that there are infinitely many critical points to this function of two variables. Now part B is quite interesting. Now we want to classify all of these points. Now to classify all of these points, we're going to use the theorem in the textbook that allows us to classify critical points either as a local min or a local max or as a saddle point. And so to do this, we need the second order partial derivatives. So to classify this, we are going to need the second order partial derivative. So we are going to use theorem 115. So first, let's write down what the second derivative is, f partial double x. That works out to be minus sine x. F partial double y. I hope you agree that this is minus cos y. And the mixed order second order partial, that evaluates to 0. Now we want to use theorem 115. And so we note that f has continuous second order partial derivatives. So this is good news. So we can use theorem 115. So the conditions of theorem 115 is met, and so now we can go ahead to classify it. Now I'm going to look at two cases. So I'm going to start off by looking at the points when p is pi over 2 plus 2 pi k pi r, where k is an integer and r is an integer. All right, so now let's start off by first evaluating d. So d at these points, we know the definition is f double x at that point times f double y at that point minus f xy at that point squared. Now in this case, this value is naught, so it evaluates to be sine x times cos y. So this is sine x times cos y, and so it evaluates to the following. It evaluates to sine pi over 2 plus 2 pi k times cos pi r. And now sine at pi over 2, or adding multiples of 2 pi to that evaluates to 1. So we get cos pi r, which is equal to minus 1 to the power r. And f double x at the point P evaluates to minus sine pi over 2 plus 2 pi k, which is the value minus 1, which is less than 0. Alright, so now we can see that the value of d depends on whether it's positive or negative, depends on what r is. So I'm going to have the following cases. If r is an odd integer, so if r is odd, then d at that point is negative, so it is a saddle point. We don't need to do any more than that. We know that if d is negative, it is a saddle point. Now, if r is even, then d is positive, and if d is positive, then and we look at f double x at the point P, that's negative, then by theorem 115, we see that P is a local maximum. So we have treated all of the points of this form. Now let's tackle all of the points of the second form, which is P is 3 pi over 2 plus 2 pi k pi r, where k is an integer and r is an integer. So points occur in two forms, this form or in the other form. So now let's have a look at this. Again, let's quickly calculate d. So d at the point P, we worked it out to be sine x times cos y. So this works out to be sine at the point 3 pi over 2 plus 2 pi k times cos pi r. This value is minus 1. This is minus 1 to the r. So this now evaluates to minus 1 to the power r plus 1. And f double x at the point P, that is minus sine 3 pi over 2 plus 2 pi k, which is minus 1, which evaluates to 1. And now we have enough information to use theorem 115. Again, if r is even, then an even number plus 1 is odd, minus 1 to the power of odd number is negative. So then d at the point P will be negative, so P is a saddle point. So this is the nice thing. The moment that d is negative, we can stop and immediately say, so P is a saddle point. But we are not done. We also have to look at the case if r is odd. If r is odd, then d at that point evaluates to odd plus 1 is even, minus 1 to the power even is 1, so it's positive. And we saw that f double x at the point P that's equal to 1, so that's positive. And so we can say in this case that P is a local minimum. And that, ladies and gentlemen, is the end of this assignment. Have a good day.